including she's the Distinguished University Professor and Chair of the Richard A. Miner School of Computer Science, and she's the director of the New England Robotics Validation and Experimentation Nerve Center. If you haven't been out there to visit it, oh my God, she has so many robots, and it's a lot of fun. She has all the toys. And if we're gonna do another telepresence challenge, I think her center could be a really great place to do it. She's also done a ton of service for ACM and IEEE, both serving as general chair for the ACM and IEEE Conference on Human Robot Interaction, and serving on the steering committee for many, many years, helping and chairing it, herding all the big cats because we're so much fun. And of course, telepresence is a large and important part of human robot interaction. So I've had the pleasure of getting to work with Holly in wrangling said cats in said conferences. And so it's really fun to get to be here at an inaugural conference together with you all to get to hear about her work. She also has some cool stuff that she's not going to talk about very much in this talk today, but you should totally ask her about. Holly was snooping around in the background during the DARPA Urban Grand Challenge, watching people, observing them experimentally.
It was a paid thing. It was snooping.
Yes, DARPA, it was legit.
DARPA contracted me to stick around.
So she actually got to see all the back of house stuff that was going on. All of the grad student teams are scrambling around, making those robots actually run, and learned a ton from it. And so as we talk about interfaces, right, for people to be able to effectively be telepresent via all these different kinds of robot bodies, she has a ton of experience there. So ask her about it when you catch her at a coffee break. All right, that. Thanks, Holly.
Thanks, Lila. So it's 25 minutes, so no, I'm not going to cover everything. I tried to pick some representative work throughout the years of some things relating to telepresence. And so, come on, computer, there we go. I put up the slide. If you've seen my talks before, I usually put up family photos. This is not all my robots, but I wanted to put up slides thinking about telepresence as a distance function. So when you look at this robots on the left, we're really looking at robots that people are, I would say, strongly co-located with, because they're wearing them, they're riding in them. As we move towards the middle, you've got more kind of classic telepresence robots, or robots that could be functioning as that, but sometimes people are in the same space with those robots. So you may be doing a manufacturing task with a fetch, you might be in a home environment with stretch, and having it bring something to you. And then there are the modified Vigo telepresence robots that Kate Sui did for her PhD. And then on the right, examples of some robots that might be used for Mars rovers or for search and rescue. For those of you who buy startup robots, the Junior I bought in my startup package 25 years ago, we just updated and we're still using it. So this is why companies go out of business, because we keep updating our robots. So let's start talking about the strong co-location first. Obviously not really telepresence, but something to think about, and the kind of the through line that I want to take in this talk is thinking about having an awareness of what the robot is doing and what is around the robot. So situation awareness, and can you predict what the robot's going to do? And I think what's particularly interesting when you start looking at, in this case, this arm-worn exoskeleton, which is by a company called Myomo in Cambridge, Mass. We also work with a ankle exo called, that's with Defy, and also Massachusetts. We have a lot of great companies in Massachusetts. I know California, you think you're the center of the world, but we have a lot of robotics too. And so I think one of the most interesting things when you've got an adapted exoskeleton is we as people adapt to our systems, but they're adapting to us. So we're trying to figure out, how can we let people know when the system is changing? Can we allow people to reject those changes? Could they request changes? And how do you do this in a way that has very low workload, that you don't have to have John's system strapped to your head all the time? I don't see John in the room, but so how do we think about workload, and how do we think about people adapting to the systems? And I think that's something that's going to happen through all of our robot systems, but it's particularly problematic when somebody's wearing a system that's changing, because all too often, if a system is adapting, sometimes we think it's breaking, it's not working like we expect because it is different than it was. So that's, you know, the kind of the co-located, not really telepresence. But as we move forward into thinking about robots like Stretch and Fetch and a scooter here. So this is a project that we have with Northeastern University. And the idea is that in the United States, when you go to grocery stores, they have scooters available for people to use if they can't walk around the stores. But they don't have robot arms in them. If you need help moving around the store, you probably need help reaching for items as well. So we're thinking about, and this is augmented reality, but kind of using a projector, how do we turn the world into the interface? So how do we basically allow the person in this sense to kind of have their intent kind of projected into the world so they can say what they want? So if you think about going through a very packed grocery store and you want to pick a particular item, it's not really efficient to look at the shelf, see the particular can that you want, and then look down at your interface, try to figure out how to zoom to that location and then select what you want. So what we're doing instead is we're using a simulated laser coming out of the projector. So you can see here, it's highlighting on all the different objects. Once the object is selected, it's on the lobster right now, the stuffed lobster. The system computes and it basically has you confirmed that you know where you, basically, is this what you selected? Because what you don't want to do is go pick up the wrong object. So that's one way to put the robot's intent into the environment. So that's our shared environment. We can also do this with our fetch robot. In this case, fetch is trying to get in this narrow space. It's going to show that it's trying to go to the right with the green, purple arrows. Then it shows that it sees the obstacle, and then it shows the purple arrows moving around in the other direction. So we can use VR, AR, kind of into the world as opposed to having to wear glasses to communicate the robot's intent and to validate what you want for your intent. But again, not quite telepresence, kind of that mix there. So now we move on to thinking about how could we actually have telepresence out in the real world. So back in 2010, so that was a long time ago. You were doing some telepresence back then too, or Lilo, yeah. We had the opportunity to take 2 different telepresence robots to Google and try them out. So 2 of my graduate students, Manjal Desai and Kate Sui, spent the summer at Google trying telepresence robots in a number of different configurations. So this was the AnyBot QB robot, which is self-balancing. Not good for power consumption. You probably don't want a robot that's going to sit at a meeting a lot of the times, have to be actively balancing, but we'll move past that. On the right is a system, Vigo. That robot has been sold to Vecna. So I think it's still available there. I don't think the QB is. So we did 5 different studies, and we wanted to see what people thought about it as they moved through the hallways. We looked at how people could use them in walking conversations, and you can see that they are different heights. The QB actually has a screw attachment on top of it, so you could change its height, but not as the user of the robot, only as people near the robot, which I think is a little disconcerting if you're in a robot and all of a sudden somebody's in front of it making it shorter or taller. And of course, there are more recent robots where you can automatically control the height of the robot, but at the time, this is what we had for height changes. So we looked at different configurations at Google, and it was pretty new to have telepresence robots at that time. QB wasn't being sold. We begged, borrowed, and we didn't steal. We just begged, borrowed, and used that. So I want to talk about one of the studies. We looked at remote users. And so these are the different groups that were there. So basically, the robots were living in Mountain View. That's MTV for Google. And then we had users, either individual users. So in the case of group 1, the person in Reston was using the robot. The group in London was using it. There was somebody using it from Zurich in group 3. And then there was a one-on-one meeting, which didn't make sense then, really doesn't make sense now, but didn't make sense then either. And then we had the single groups there. And so some of the groups were engineering, some of the groups are non-engineering, because we wanted to make sure that we weren't working only with engineers, because we thought that might be a bit of a skew. Mostly we were going into a weekly meeting with these. We made them available, people didn't have to use them. There was some discontinuation. So for example, team 1 used it for the 60-minute meeting and then never did again, but they started to use it for their daily stand-ups. So we were trying to not disturb people as they did their work, but yet, kind of do some robotics in the wild. So we had asked the remote team members how they felt. And only teams 3 through 6, the users responded on this one. But it was interesting that for the person controlling the robot in team 3 and 6, they felt like they were more involved in the meeting. They were more actively engaged. The meetings were more effective, and they wanted to continue to use them. So interestingly enough, on team 6, the team member had actually been at Mountain View and was now remote. And they actually asked if they could be using the robot for coffee breaks. So less for meetings, but they wanted to go see their friends, right? They used to be in that site. So we did find a correlation between people who had already been in Mountain View wanting to use the telepresence because they had been there, they knew it, they wanted to be there. And I think it's worth saying, I'm talking about a study from 2010. Telepresence robots did not do well in the pandemic, right? They didn't do well coming out of the pandemic. So it seems like telepresence robots may not be what we thought that they were going to be. We thought they were great, but then we all got into Zoom and we all figured, this is pretty good. But maybe there are cases like the person who leaves the office and wants to have those informal breaks that we can provide that for, or allow people to go to museums or other things where it makes a difference to have an embodiment, whereas on our meetings, Zoom is fine. Now, interestingly enough, the teams were also surveyed, and they did not see their partners as being more involved or engaged, and they found the robot to be a little bit distracting. They didn't want to continue to use it, so they were neutral on the distracting. So the people remote thought, this is great, I'm there more, and people who were there were like, eh. There were anecdotal things in the days before we all had remote work. People felt like their bosses knew they were there if they had a robot, that they had a physical presence, that they weren't just there on the telecom system. So there were some values to the telepresence system, but it didn't come out as strong as we thought, and the group didn't do that well with it, and they didn't like it as much, which isn't surprising, right? Think about your hybrid meetings where you're the only person on the hybrid and everybody else is in the room. Is it better if you're on the screen or in a robot? Maybe with a robot, I could go roll up to somebody's chair and go, no, seriously, I'm here. Hello, hello. But telepresence robots, I don't think have sort of found their way right now. Layla's nodding along, having worked in them for a very long time as well. So we did look at telepresence for people with disabilities to go to museums. So this is Kate Sui's PhD research. She's now at TRI, running HRI there. And one of the things that we did is we actually looked at using these artbotics exhibits. So we had a education program for middle and high school students, as well as for undergrads not in computer science, where they could build interactive art projects to learn how to program. Because if you haven't heard my spiel, in computing one, we teach people to do loops by computing compound interest. Why? Why are we doing that? Give them a robot, have them make a pattern, and then do spirograph, right? So there are many better ways to teach computer science. But for this case, if we're gonna have a telepresence robots going to a museum, just going up and looking at a painting on the wall, is that different than looking at photographs of it or looking at a good rendering of it? So we wanted to have that. So we took the standard Vigo platform on the left and augmented it with Koyu with more cameras and then some status lights in the flowers. Kate spent a lot of time with a few other people designing the Hawaiian shirt. Actually, the first version had a tie on it, and everybody would always say, but she's a woman. Does she want to have a tie on a robot? And Kate would wear ties, but we decided to go with something that the world perceived as more unisex by moving to a Hawaiian shirt. So I'm not sure if Mark was already wearing them at that point. So I don't know if we were the first. He was. Okay. In any case, so we had status in there. And one thing we wanted to do was make it so the robot didn't have wires hanging out all over the place. It was a representation of a person going into the world, and we didn't want to have things sticking out all over the place. We need to provide a better field of view. This is something that the occupational therapist we were working with was telling us about people who are his clients, that if you have a very narrow field of view, it's going to be much harder for them to drive and know where they're going. And it's not going to be a great experience, right? I think in telepresence, people aren't surprised that having better fields of view is better. So you can see that the standard camera on the right there has a very narrow view, whereas you can see the entire exhibit here with the 3 cameras. These are the interfaces for it. And so we try to, I'm an HRI person, and I'll claim that all robotics is human-robot interaction. If you want to have an argument, I'll give you epsilon. But in any case, so we have our interfaces here. Let me show you them running. The artbotics pieces, there's this idea that as you get closer to them, they do different things. If you go closer to the monkey, it'll flip faster. If you move farther away, it'll slow down. And different pieces do different things. Sunflowers will look at you in different locations. So when we're using the interface, it'll show the direction of the robot movement. It shows the base, the wheels move, well, the graphics move, to show you that the robot is moving. And then when you're near the exhibit, it tells you you're moving towards it. When you're at it, you have controls to actually move closer to it, so you can make it activate, or you can move to other exhibits that are nearby. So let me show you the video of this. So on the left, we have the exhibits. It's a narrow set of exhibits. And the user's going to pick to go to monkey. So it says moving to monkey. It's showing, you can see on the base, it's showing how it's going to travel. And then, I don't know if you can really see it, but the wheels are actually moving in the graphic there. And you can see the outer view and then the user view. So you can see the big wide view. It's going, Kate's going to sit down so she can talk. So we were trying to make it be a social experience for the user as well, so they're not just going and interacting. The buttons that show there show the positions along the exhibit that you can use. You can pick the one that you want to go to, and it'll pull it up. And then once you're there, you can turn the robot, or you can move closer forward or move to one of the other positions. So we were trying to really allow someone to have an easier way to get there. You'll see the buttons are really large. It was designed so that we could actually put a key guard over it. So if people have trouble with fine motor skills, that they could have a key guard on top of the screen to go through the hole into the button that they wanted. That's why the buttons are so large. So to finish up with this, I want to talk about telepresence for when we have situations where we can't be with our robots. So whether it's the search and rescue type of situation, whether we're thinking about Mars rovers. So one of the things that we had started studying, and this is with Aaron Steinfeld at Carnegie Mellon University back in around 2011, was how do people trust robot systems, particularly when they're not in the room with them. So I joke that I'm an anti-social roboticist. I don't think we actually know enough about robots to truly be making social robots at this point. So none of my robots, well, they do have faces when I buy them, but I don't intentionally buy robots with faces. I don't think we're there yet. So we were looking at, as a person is working with a robot, the robot could be fully autonomous or semi-autonomous. We forced them to go into the autonomous mode, because if they didn't go into the autonomous mode, the robot couldn't go fast enough for them to earn the bonus. One thing that we found while doing the study is that you have to have some amount of risk involved. And we talked about this yesterday in the talks as well. If there's no risk involved, then John has said, you give your undergrads $20 when they walk in. They didn't have $20 when they did walk in, right? So you have to have some sort of risk in order to get them to think about the scenario more, to really buy into it. And obviously when we're controlled by institutional review boards and also humanity, we don't want to actually put them in real risk situations. So in this study, we were looking at if we controlled when there were failures. On the top right, we had 4 conditions. So in 1, reliability A, the robot worked perfect all the time. In B, we had 2 failures, 1 early, 1 in the middle. In C, we had 2 failures right in the middle. And then on D, we had 2 failures in the middle and the end. And we were really interested in the timing of failures and how that influenced people's idea of trust, which if you think about it, if you're put into a group in a class and you're working with people, if you start working with this person you don't know, and they flake on you the second day, there's no trust for the rest of the semester. But if it went pretty well for the first few weeks, and then maybe they flake a little bit, maybe you're willing to cut them a little slack, maybe they tell you, oh, my grandmother died. Classes and midterms are the worst time for grandmothers. So we were curious as to what happened. And so when we were looking at real-time trust, the purple line is the reliability A. And basically people had increasing trust as the robot continued to work. And the failures that we had is the robot had to drive around these boxes. And we told the person, you have to read the labels. So the labels are, for the first half were white, second half are black. The words right are buried in both of those. We didn't want people to see the shape of the word from far away, so we buried it in letters. And then we told people that the robot was reading the barcode at the bottom. Not a single person asked why there was only 1 barcode for the robot and 2 for the people. So they suspended their disbelief there. So they had to drive the robot. If the robot was going to go the wrong way around the box, they had to take over. So they were penalized for that. So it was a complicated scoring system. In this particular experiment, we gave some feedback, which I would never do it now. We called it non-semantic and semantic, but of course a plus sign and minus sign is semantic, so let's ignore that. But the idea was, if the robot tells you, I'm about to fail, will it be better for workload? And so we had a, basically, I'm good, I'm not sure, and I'm about to fail indicator. And so they had to follow the path, do the secondary tasks, because of course you always have workload tasks, and you want to make sure that they have situation awareness. So are they seeing things in the world? Are they paying attention? And we did 2 experiments. We did the dynamic reliability ones, and then we did dynamic reliability with feedback and compared those. And one thing that we found is that when we look at these 4 reliability modes, if you're using a typical end of run measure, we were using Mirror. There are new measures of trust now, but Mirror also mimics that. You can see that when the reliability was perfect, they had high trust, but when the failures happened in the other three didn't matter at all, right? Because it's kind of a recency. You get to the end and you're like, yeah, it failed sometime, but you're not thinking about it. Whereas the area under the trust curve measured, and it could see it was very sensitive to an early failure. So the fact that we were looking at real-time trust was very effective, and we could tell if people had lost trust, which if you can tell that they've lost the trust early on, you can work to rebuild that trust. So if that person flaked on the project, maybe they do a lot extra for the next one, and you're like, okay, good, we can still work together. So one thing about feedback for this particular paper, we didn't actually find any difference in trust, and I think it's because we added to the workload. We basically had a robot, you had to pay attention to it going, I'm good, I'm good. Why did we do that, right? So you could look at it without doing that. I think it would actually be better. And we did see some increased mode switching because of that middle one of I'm not sure. So they had to kind of check on the robot a bit more the way we provided feedback. So the last project I wanted to talk about is looking at kind of thinking about VR for controlling a robot versus a 2D mouse and keyboard. And the 2D keyboard and mouse really comes from the Dark Robotics Challenge that Leila had alluded to. So Tash Padir, Rob Platt, and I had gotten a Valkyrie robot back in 15. We went back to NASA in 2020. And shortly after we got the Valkyrie robot, Tashkin and I, the center one, had gone to the Savannah River site, and we were looking at a mock-up of glove boxes where they had made plutonium for the NASA missions that they were getting ready to clean up. And the really cool thing about the Department of Energy is they spend 10 years planning to do missions, which is exactly the time to get roboticists in, because we can actually do some development, as opposed to what John had done on 9/11 and just called everybody and said, bring whatever you have, which is fantastic that he was able to do that. But imagine if people, well, if you had a warning, hopefully it wouldn't have happened. But you know what I mean? If you have time to prepare, then you can develop better systems. So we started thinking about how can we work in glove boxes, and Tashkin was really focused on planning for contact manipulation. So could you, as a human, if I have to reach far, I might lean on something. With our robots, we don't usually let them touch anything, but we do that all the time as people. So could we have the robot leaning on the glove box as it's reaching into the glove box more? Could it take its leg up because it's putting more of its weight on the glove box? So that was the part that Tashkin was focused on, whereas we were focused on looking at how we could do the control within the glove box. So we started off doing control interfaces, our very early work on Valkyrie. But then we moved it over to Fetch. The pandemic hit as we were about to do a lot of studies. So, and then NASA had to take it back after 5 years. So we have these functional waypoints for our Fetch robot. So we can basically tell it where to go. On the back of it, we can say, once you get there, we want you to be at a particular height. So we can set the height on the back of the robot. Fetch has a body that goes up and down. So you can see there on the left a little bit better of setting it. So the idea is that you go to that waypoint, and when you get there, you go up or you go down, and then it shows you where it's moved. Manipulation, same sort of thing, except you're setting where you want the gripper to be in the world. So this is basically doing kind of a pre-planning. You're telling the robot where you'd like it to go. It's going to demonstrate the plan for you, and then actually execute the plan, which is a lot of what was happening in the Dark Robotics Challenge as well. If you saw, maybe go by, when one of those was placed, it was yellow. We're actually telling the person that it's already out of range. When we do the planning later, it'll go red to tell them that it definitely is out of range, but we are giving that information there. This is the plan visualization as you go through, and it's showing you how it's moving through. So on the right, it quickly redid. So for the comparable 2D interface that we used, we actually used a 2D interface that was from the Dark Robotics Challenge. It was from the CMU WPI team. So Tash and Peter had been at WPI and part of that team. If you've ever heard Chris Atkinson talk about his team at the Dark Robotics Challenge, kept saying, no falls, no resets, no falls, no resets, no falls, no resets. And so they came in third place, but they did have no falls and no resets, which is none of the other top teams had. So we wanted to use that interface. Yes, it's old, but it was a good interface, right? It had been shown in a competition to work. But the worst thing you want to do when you're doing comparison is to use a straw man. So we picked that up. So you have to, set where you want the arm to go on that. So it's not quite as nice as the VR interface, but on the other hand, it's well tested and people have been trained for it. And so we had two tasks, navigation tasks that had to go and look at buckets. There were land seas in the buckets, and they had to tell us which direction they were facing in. The reason we did this is we wanted them to have to put the body of the robot up and down. So the buckets are at different heights. As they moved around, they had to yell at the robot as they get over to that other side. We gave them scores for basically seeing the target in the navigation task, and then they get points against them for collisions if they hit anything in the environment, or if the experimenter said it was dangerous and hit the stop button, that was also considered a collision. On the manipulation task, they had to stack Jenga blocks, and they were not actually penalized. You'll see here as the robot goes in, the arm is going to get low and they're almost leaning on the table. We didn't penalize that as a collision if they were using the table kind of as a rest. If they knocked over the entire stack, then it was. But just coming into contact with the table was not considered a collision. So we ran 28 people. The condition that was between subjects was whether they were using the VR interface or they were using the 2D interface. Everybody did manipulation and navigation 3 times on each one, and they alternated. People were given training in both of those interfaces. One of the interesting things is we typically allow people to train as long as they want until they tell us they're comfortable. No one in the 2D condition timed out of training. We had a couple people in VR use the entire time of the experiment to train. Yeah, so, yep. Whether they were enjoying it, because you never really know what their intent, but we had to exclude a couple people because of that. So we thought that VR would be more usable. And in this case, there actually was no significant difference on that one. There was a little bit, but it wasn't significant. We had also hypothesized that people who were using the VR interface would have a lower workload, which did not bear out. We thought that people would improve more greatly with VR than they would when they were using the other interface, which did bear out. With keyboard and mouse, people were kind of at their peak at the beginning, and VR, they were getting better over time, which does kind of raise that question of training. And so one thing that we found as we were doing this is that, although it wasn't significant, there were fewer collisions. So we're kind of hypothesizing that if you have something where people are navigating and a collision would be really, really bad, it's probably worth training people on the VR. But if they can hit and you don't worry about it, then probably the 2D would be a lot faster to start up on. But I think that comes out to the heart of all the talks that we've seen. You know, the videos yesterday, I don't think he's here to correct me, but I think Osama was driving during most of them, right? So he's super well trained to use that. What happens if somebody who isn't as well trained goes to use it? How does that system work? And a lot of the work that I'm doing, I think I'm taking what I would call kind of the anti-NASA approach. So NASA will design something and they're just like, we can train people forever. Doesn't matter how well designed it is, we will just train them until they're super good at it. And I think a lot about what happens if somebody's a novice. How do we get people in to use these systems right away fairly effectively? So coming back to all of these, some of the open questions I think related to Telepresence and HRI that I've been thinking about are, you know, how does HRI change as systems become more capable? And I'm using capable and autonomous there very intentionally. There's a lot of talk, particularly in the military, about having autonomous robot systems. I truly believe that we do not want autonomous robot systems. We may want capable robot systems. Autonomy basically says you can make selections, right? So we want robots that are very capable, but I would argue that nobody wants an autonomous private in the Army. And I'm not sure we want fully autonomous robots either. But as they become more capable, if I can just say, pick up that Jenga block and move it, it's going to do it all the time, then what changes with the HRI? Can I say make a stack? Do I have to have more control? What do I need for situation awareness? Should I be monitoring? Should I not be monitoring? Should it just tell me when it's about to fail, when it has failed? So are we living in a land where HRI is always going to have to adapt? Or is this some sort of steady state? I don't know the answer to that. And I think this may just be an age thing, because I'm starting to think that time is actually a factor in human-robot interaction. I think these changed how we interacted with robots. Not just because we finally had cameras that we didn't have to build frame grabbers for, but because, so my student Mark Musiri that John had mentioned yesterday, he was looking at multi-touch for groups of robots. And one of the first studies he did on the multi-touch is he had basically had a series of PowerPoint slides and said, show me how you move the red robot to area A. How would you move these 2 robots? To look at how people would come up with gestures for that. So we can kind of have user design gestures. Not natural. It's not natural that we click. We were taught to do that by the computer. When he did this, it was just as the iPhone was coming out. Anybody who was an early adopter and had an iPhone, when he said, how would you zoom in on that map, went, And anybody who didn't have an iPhone went, don't know what to do. So we definitely take things from other parts. So time does make a difference in HRI. How can we make that an input to our system? Or are we always going to sort of be making bespoke interfaces? How do we account for people's experience or lack thereof? So are we designing for novices, for very experienced people? Can I learn something from one system that translates to another? Can our robot say, oh, I'm like this other system? Can they try to convey some state to us? And then really, how do we reduce cognitive load when we're improving people's situation awareness? It is really hard to have an awareness of what's around your robot system. And if you're in that search and rescue scenario, that picture that John was showing of that woman trapped under a building, if you're taking a robot in there and you're going to ram it into something that's going to cause a secondary collapse, you could kill somebody. You need to have good situation awareness. And how do we do that? And how do we do that fast and effectively and really make sure that it's correct? Thank you.